Find a parameterization or a vector equation for the line of intersection of these two planes. Okay. So let's think about what's happening graphically first. We've got two planes in space. If the planes are not parallel, then they have to intersect at some place. We'll just draw them like this. Some point at some line they are intersecting, and we want to find the equation of the line where they intersect. We want it as a vector equation. The way we're going to approach this problem is we're going to think about finding the normal vector to each plane, normal to this one, and then the normal to this one. And the idea is that if you take those two normals and find the cross product of those two normal vectors, you're going to get a vector that is perpendicular to both and therefore parallel to the line of intersection between the two planes. Let's go ahead and find this vector here, call it V. And that's just going to come from taking the cross product of the two normal vectors. We'll write out the cross product formula. I, j, and k in a matrix. We're going to take the determinant of that matrix. So the way you find the normals, it doesn't matter what order you do, but it's just the coefficients. So x minus 1 and minus 3. Just make sure all your variables are on one side of the equation before you do this. We're okay in this sense. So 2, negative 1, and negative 3. Negative 1 and a negative 3. And the normal for this plane is negative 1, 1, 1, negative 1, 1, 1. So the determinant is going to be I, the I unit vector, times the determinant of these four numbers, negative 1, negative 3, 1, 1, j, times the determinant of these numbers, 2, negative 1, negative 3, and 1. How are we finding that? We're just crossing out the row and column that j is in, and then taking the determinant of what's left. And then finally, we'll do the same thing for k, plus k, and we're crossing out this row and this column, taking the determinant of what's left. And we have to remember, just part of the formula, you have to put a negative here before the j. Now let's go ahead and calculate this. This is I. So remember how this determinant goes. It goes these two numbers, and then you subtract, well, these two numbers multiplied, and you subtract the product of these two numbers. So we'll get negative 1 minus negative 3, which is plus 3, minus j, and same thing here. 2 times 1 is 2, minus negative 1 times negative 3, so that's minus 3, plus k. 2 times 1 is 2, minus negative 1 times negative 1, so that's minus 1. And so simplify this a bit and get 2 minus 3 is negative 1, and then the minus here makes plus k times 1. And then plus 1k. So our vector is 2, 1, 1. This is our direction vector. Our line is going to be some initial vector, we'll call this v naught, plus t times our direction vector. All we have to do now is find this v naught vector. Well, the v naught vector can just be treated as a point that lies on the line of intersection, and there are infinite points that lie on this line of intersection. It's very easy to find one. So let's look at our two equations. 2x minus y minus 3z minus y minus 3z equals negative 2, and negative x plus y plus z equals 1. Okay, so you are allowed to pick a single letter to arbitrarily plug in a number and then figure out what y and z are that go with that number. So we're going to choose x being 0, and we're going to find the y and z that satisfy these two equations. So if x is 0, then the first equation becomes negative y minus 3z equals negative 2, and the second equation becomes y plus z equals 1, because both of these just disappeared when we let x be 0. Now we just solve these two equations for one of the variables. If we add these two equations, you can do addition, or you can do substitution, you can do elimination. We're just going to add these two equations so that the y's cancel, and we get negative 2z equals negative 1. So this tells us that z is equal to 1/2. We've got x equals 0, z equals 1/2. Now we have to figure out y, and you can just plug it into either equation. Let's look at this one. If z equals 1/2, then y has to be 1/2 as well. So these three values together make up a point, and we're going to treat that point like a vector as our initial vector. So finally, our line, this point becomes our initial vector, so we'll just write that. 0, 1/2, 1/2, plus t, and t times our vector from before, 2, 1, 1. Typically, you have to give the domain of t. I'm not sure if you have to here, but we'll just do that. So t is between negative infinity and infinity if it parameterizes the entire line. Next question. Consider the function f of xy given by this equation. Find the critical points, classify each critical point as a local min, local max, or saddle point. We know how to do this. We've done this a bunch of times now. First thing we have to do is find the first partial derivatives, so fx, and this is equal to 3x squared plus 6x, and fy is equal to 3y squared minus 6y. Now we set these equal to 0, find the critical points. Factoring this, we get 3x times x plus 2 equals 0. So x equals 0 and negative 2. From the second equation, we'll get 3y times y minus 2. And so we get y equals 0 and y equals positive 2. This gives us 4 critical points. We have 0, 0, 0, 2, negative 2, 0, and negative 2, positive 2. These are our 4 critical points. That's part A. And the second part, the more tedious part, is testing these points as mins or maxes or saddle points, or neither. The way we do that is we have to take the second derivatives, the second partial derivatives. So let's do that. fxx is equal to 6x plus 6, and fyy is equal to 6y minus 6. And finally, the mixed partial, fxy or fyx, depending on how you choose to do it, doesn't matter, is equal to, in this case, 0. X is not having y's in it, so when you take the partial derivative with respect to y, everything disappears. And so now we're going to define our discriminant. Remember, the discriminant is a function of x and y, and it's equal to the second partial derivative with respect to x times the second partial derivative with respect to y minus the mixed partial derivative squared. And let's evaluate this at all the different values. So the discriminant evaluated at 0, 0 equals, and when we plug in 0 for fx, we're going to get 6. Plug it in for y, we're going to get negative 6 minus 0. And that is a negative number. And remember, when you have a negative number, that's the best case because this is automatically a saddle point. No more work required on that one. Now, discriminant at the next value, 0, 2. So you plug 0 in for fxx, and you'll get 6. You plug 2 in for fyy, and you'll get 12 minus 6 is positive 6, which is a positive number. When you have a positive number, you have to do a bit more work. You have to evaluate the second derivative at that critical point. So at 0, 2. And we already found this actually. This was 6, which is a positive number. When the discriminant is positive and fxx evaluated at the critical point is also positive, this means we have a min. Local min. Two more. Discriminant at negative 2, 0. Now we're plugging in negative 2 for x here, and we're going to get negative 6. Plugging in 0 for y, get negative 6. And this is a positive number. It means we have to do a bit more work, so we check the second partial at x again at the new critical point. Again, we already found this. This was negative 6, which is a negative number. When you have a positive discriminant and a negative number, that means a local maximum. Okay, and then last one, discriminant at negative 2, 2 equals, if you plug in -2 here, we'll get -6. Plug in 2 into the fyy, and we get +6, which is a negative number. Again, that's the best case because we automatically have a saddle point. So we've classified all 4 critical numbers as mins or maxes or saddle points. If you needed to find the z values, or the output, you would just take those numbers and plug them back into the original function, this thing here, and get the corresponding z. That's just busy, tedious work, so we'll skip that. Okay, next problem. Consider the iterated integral y equals 0, from y equals 0 to 2, x equals y to 2, function. Sketch the region of integration, clearly label each part of its boundary with the appropriate equation. So if we look at this integral, we'll talk about that in a minute actually, so let's just graph the region first. Now this is a dx dy integral, so what that means is the inner bounds are functions of y, x equals some function of y. So x equals y, what does that look like? Well, that's just this graph. And x equals 2 is a vertical line, 2. And then the y bounds are going from 0 to 2, to here, to here. This is our region right here. So we can label this. This is y equals x, and then this is x equals 2. And the bottom we can call y equals 0. That's part A. Now part B, if we look at this integral, integrating cosine x over x squared is actually impossible. There's no antiderivative that we know of for that function. So when we're going to reverse the order of integration and hope that that makes it actually possible to integrate. Spoilers, it does. So we're going to rewrite our integral. Now the function always stays the same. You never change this. But this arrangement will change. This will be dy dx. And now we have to change the bounds on our integral. It's never the case, well, sometimes it could be, but it's not in general the case that you can just reverse these two integrals. So we'll have to think about this. We have dy first, which means these bounds have to be function y equals some function of x, and then y equals some function of x. And these outer bounds are going to be numbers. So the lower bound, the region that, or the section that bounds our region here is this. We're doing dy, so we're thinking about top and bottom, versus dx, where you're thinking about right and left. So top and bottom. On the top, we are bounded by the graph y equals x, and on the bottom, y equals 0. And then for dx, we're bounded on the left by x equals 0 to x equals 2. And then the function is the same. Okay. Now, we can try to integrate this thing. We're integrating dy first, so all of this x stuff is constant, and we'll just integrate y. So we get y squared over 2 times cosine of x divided by x squared dx. we're going to evaluate this inner integral on its bounds from 0 to x. So 0 to 2. And then plugging in x for everywhere we see y, we'll have x squared over 2 cosine of x over x squared. That's the upper bound. Minus the lower bound, which is just 0. We're plugging in 0 for y, so this becomes 0. Okay, we can clean this up a bit. X squareds cancel, which is real nice. Cosine of x over 2. We'll pull the 2 out front, so we'll just have 1/2 in front. X. This is a real easy integral. This will be sine of x, well, 1/2 sine of x. And evaluating that from 0 to 2, and then plugging in, we have 1/2 sine of 2 minus sine 0. Sine of 0 is 0, sine of 2, well, that's not a unit circle value, so we will just leave that as sine of 2. And this is our answer. Okay, next problem. Compute the double integral over this region where D is a circle of radius 2 centered at the origin. Hint, use polar coordinates. Okay. This looks like a very ugly integral, and you wouldn't want to do this in rectangular coordinates, so we're going to try polar. Always a good idea to graph a region, though. It's not a unit circle, excuse me, it's a circle of radius 2. This is our domain, our domain of integration. And remember that when you switch to polar, the identities we use are, let's see, x equals r cosine theta, y equals r sine theta, and x squared plus y squared equals r squared. Well, this makes this problem incredibly convenient because x squared plus y squared is just r squared, so we'll plug that in. Cosine, the square root of r squared is just r. That's real nice. On the bottom, same thing, square root of r squared, which is just r. And then remember that when you change to polar, it doesn't just become dr d theta, it becomes r dr d theta. We always introduce this extra little r here. You don't have to understand why. If you take 20e, you'll see where that comes from. But for now, we'll just accept that we have always introduced this r every single time we change to polar. And that's perfect because this is going to cancel with this. And now we have to figure out the bounds. Now these are bounds on r and theta. Looking at this circle, it's very easy to see that the bounds on r are from 0 to 2, because our radii can go from 0 to 2. And then our angle can vary from 0 to 2 pi. So let's integrate this thing. An antiderivative of cosine r is sine r, evaluated from 0 to 2. Still got this outer integral. D theta. This becomes sine of 2 minus sine of 0. Sine 0 is just 0. and then we're going to integrate sine of 2, which is just a constant. We could pull that out if we wanted to. Let's do that. Sine of 2 times the integral from 0 to 2 pi of d theta. So what does this become? Sine of 2 times just theta, evaluated from 0 to 2 pi, which is equal to sine of 2 times 2 pi minus 0. Our final answer is just sine of 2 times 2 pi. Don't try to say this is 4 pi because it's not. It's just 2 pi sine of 2. Weird number, but it's not a unit circle value, so you just leave it there. And that is our integral. Next problem. Find the points on this sphere that are closest to and farthest from the point 6, 6, negative 3. Be sure to state which of the points is closest and which is farthest. Okay, so before you try to do any Lagrange multipliers or any type of optimization problem that you did at the end of the course, there's a faster way to do this problem actually. Let's draw a picture and think about what's happening. So we've got a sphere here of radius 3, because this is 3 squared. So 1, 2, 3, 1, 2, 3. That's not the best picture, but you get the idea. And then we have a point 6, 6, negative 3. And then this doesn't matter all that much, but just out here somewhere in space. And we're trying to decide what point on the sphere is closest to that point, and then what point on the sphere is farthest to that point. Think about this picture in 3 dimensions, and think about a line or a vector that connects the origin to that point. It's supposed to be a 3-dimensional looking picture, but you've got a vector that goes from the origin to that point. It should be reasonable then to conclude that the point which lies on the sphere that is closest to this point out here in space is the same point that is the same point where the vector is intersecting the sphere, right here. Just think about that for a minute. The point out here is in space. We've got our origin point. If you build a vector between the origin and that point in space, it's going to pass right through the sphere at this point on the sphere that's closest to the point in space. So let's think about this point in space out here as a vector. Call it V. 6, 6, negative 3. Now this vector has some length. We don't know what the length is. At least not yet. We can find it if we need to. What about this part though? This part of the vector, we do know what that length is. That length is 3. Why is it 3? Because that's the radius of the sphere. This vector goes from the center to the edge, which is 3 units because it's a sphere of radius 3. So that portion has to be 3. So what we'd like to do is take this vector that's going from the origin to the point and rescale it so that it's only 3 units long. If we do that, then the vector is going to terminate at the point that we're looking for. So let's take our vector, let's multiply it by some constant, and we multiply it by this constant, and we'd like for the magnitude of this quantity, for this vector, to be equal to 3. If we can get that, we're all set. Now there's a property of vectors that says the magnitude of a constant times a vector is equal to the absolute value of the constant times the magnitude of the vector. And again, we want this to be equal to 3. So our constant is going to be 3 divided by the magnitude of the vector. So let's find the magnitude of the vector. Well, that's just going to be magnitude of v is equal to the square root of the component squared, so 6 squared plus 6 squared plus negative 3 squared. Let's see. This is the square root of 36 plus 36 9, which is equal to the square root of 72 plus 9 is 81, and that's just equal to 9. So our c, our absolute value of c, is equal to 3 over 9, which is just 1/3. Remember, when you're solving an absolute value equation, you can have c is equal to positive 1/3 or negative 1/3. That's going to come into play here in a second. So remember, we were rescaling this vector. Let's do that now. 1/3 times this vector, 6, negative 3, is going to give us the vector. Let's see, this vector becomes 2, 2, negative 1. Now this vector here now represents the vector going from the origin to the point on the sphere. So this vector is actually just the point that we're looking for. Now this is the point that is closest to that point out in space. Now the negative c value is going to give us the opposite. If you rescale this vector and then flip it around, it's going to go back and touch on the opposite end of the sphere. So our other answer is negative 1/3 times that vector, 6, 6, negative 3. And that's going to give us negative 2, negative 2, positive 1. And again, we'll treat this as a point, 2, 2, negative 1. Or, excuse me, negative 2, negative 2, and positive 1. And this is our farthest point. Okay. Next problem. Gradient of a function g of xyz at the point negative 3, 4, 5 is this. Find the values of the partial derivatives gx, gy, and gz at this point. So this question is really just asking you to understand the different parts of the gradient. They tell us that the gradient of g evaluated at the point negative 3, 4, 5 is equal to negative 2, 1, 2. But if you remember how to calculate the gradient, it's actually just a vector that contains the partial derivatives x, y, and z. So right away, you just get g of x equals negative 2. Sorry, partial derivative of g with respect to x is negative 2. Partial derivative of g with respect to y is 1. The partial derivative of g with respect to z is 2. That's it. That's probably 2 points. Very easy question. Just have to understand what exactly the gradient is. And that's part A. Now part B says, find the maximum rate of change of g at the same point that we've been talking about, and the unit vector in the direction in which the maximum rate of change occurs. So the maximum rate of change is just the magnitude of the gradient. So let's just take the magnitude, write that out, the magnitude of the gradient vector. In our case, the gradient vector was this thing, which is the square root of -2 squared plus 1 squared plus 2 squared, which is the square root of 4 plus 4 plus 1 is 9, which is 3. So this is our maximum rate of change. And then they ask us to find a unit vector in the direction in which the maximum rate of change occurs. Well, the direction in which the maximum rate of change occurs is the gradient. That's the whole point of finding the gradient, is to find the direction in which you get the maximum rate of change. So if we want the unit vector, all we need to do is rescale the gradient so that it has a magnitude of 1. Remember, the way that we did that is we would just multiply the gradient by 1 over the magnitude. Now, in our case, we already just found that. So we have 1 over 3 times the gradient, -2, 1, 2. And you can distribute that if you like. You don't have to, but we'll do that. -2/3, 1/3, 2/3. So this vector here is still in the direction of the gradient. It's just rescaled so that it has a magnitude of 1. That's part B. Part C says find the rate of change of g at that same point in the direction of this other point. In the direction of the point means in the direction of the displacement vector from -3, 4, 5 to -1, 8, 1. All you need to do is find the vector that goes from this point, initial point, final point. We remember how to make vectors between 2 points. It's just the final point minus the initial point. I'm going to use some poor notation here, but it's just going to be the final point. -1, 8, 1 minus -3, 4, 5. Make sure we got that. 1, 8, 1, -3, 4, 5. So when we do this, we're going to get a displacement vector. -1 minus -3 is -1 plus 3, which is 2. 8 minus 4 is 4. 1 minus 5 is -4. This is our displacement vector. Now what they're asking us for is the rate of change of g in this direction. Well, that's the directional derivative. Remember how to calculate that. That's just the gradient. And you take the dot product of the gradient with a unit vector in the direction that you're trying to go. So our gradient was, and don't use your rescaled gradient from part B, just use a regular gradient. -2, 1, 2. We're going to take the dot product of the gradient with this vector that we just found. 2, 4, -4. But we have to rescale that vector to be a unit vector. So we need the magnitude of this vector. Let's call this u. And so the magnitude of u is the square root 2 squared plus 4 4 squared plus negative 4 squared, which is the square root of 4, 16 plus 16. That's 32 plus 4 is 36, which is just 6. So that's what we have to rescale the unit vector by, 1/6 right there. Now don't try to distribute it in, because dot products have the nice property that you can pull this constant out front. So we'll have 1/6 times the dot product. Now the dot product is just multiplying the respective parts. So 2 times negative 2 is negative 4. 4 times 1 is 4. Negative 4 times 2 is negative 8. And you just add these. And so our final answer is negative 8 over 6, or negative 4/3. That's the rate of change in the direction vector, or in the direction of that vector we just found. Next problem. Let f of x be defined by this function here. Find an equation for the tangent plane at this point. Use a linear approximation to estimate this value. Okay, so the equation for the tangent plane is z equals z naught plus f x evaluated at that point. So 2, 1, times x minus, well, we'll write it in general first. Evaluated at x naught, y naught, times x minus x naught, plus the partial derivative with respect to y, evaluated at x naught, y naught, times y minus y naught. I already have most of this stuff. Z is equal to z naught, well, that's just given, 0. If you weren't given that, you can just find that by taking 2 and 1, plugging them in here, and getting out the z value. So 0 plus, now the partial derivative with respect to x is 1 over 2x minus 3y times 2 by the chain rule, times x minus, I haven't evaluated it yet, but times x minus 2, x naught, y naught, z naught, plus the partial derivative with respect to y, 1 over 2x minus 3y times negative 3. And that's times y minus y naught, which is 1. And then again, we have to evaluate these two derivatives at that point. We'll get z equals 0 plus 2 over, and when you plug in 2 and 1, you're going to have 4 minus 3, so just over 1, x minus 2, same thing here, minus 3 over 1, y minus 1. Let's rewrite that one more time. 2, x minus 2, minus 3, y minus 1. This is the equation for our tangent plane at that point. Now, the tangent plane is the same thing as a linear, well, it's used for linear approximations. So f of 1.9, 1.1 is just going to be approximately 2 times 1.9 minus 2 minus 3 is 1.1 minus 1. We're just taking these numbers and plugging them into our tangent plane, and then we'll just simplify this. 1.1 minus 2 is negative 0.1 minus 3 times 1.1 minus 1 is 0.1. This is 2 times negative 1/10 minus 3 times 1/10. Which in total becomes negative 5/10. And that's it. That's your approximated value, approximated z value at 1.9 and 1.1. Last problem. Particle follows a path given by r of t equals 4 cosine t I 4 sine tj plus 2t squared k. Find the position of the particle at t equals 0 and t equals 2. So at t equals 0, well this here is a position function. So if you need to find the position vector at time equals 2, you just plug in, the position vector at time equals 0, you just plug in time equals 0. So r of 0 equal to 4 cosine of 0, 4 sine 0, 2 times 0 squared. And this vector is just 4 cosine of 0 is 1, so 4 sine of 0 is 0, 0, and then 0 here as well. The same thing for time equals 2. We're going to get 4 cosine of 2, 4 sine 2, and let's see, 2 times 2 times 2 is 8. Cosine of 2 and sine of 2 are not unit circle values, so you can just leave them as that. Now, that's part A. Part B says, find the speed of the particle as a function of t. So, you can't get the speed without having velocity, and you can't get velocity without having position. So how do you get velocity from position? Well, the velocity is just the derivative of the position with respect to time. And so we're just going to take the derivative part by part. The derivative of 4 cosine t is negative 4 sine t. The derivative of 4 sine t is 4 cosine t. And the derivative of 2t squared is 4t. This is the velocity vector. Remember that speed is the absolute value of velocity. In vector form, that means that speed is the magnitude of the velocity vector. So magnitude of the velocity vector works the same way as you've done it before. This is the square root of every component squared. That's the first component squared plus the second component squared plus the last component squared. And we can simplify this. This is the square root. This is 16 sine squared of t plus 16 cosine squared of t plus 16 t squared. Factor out the 16 from sine squared plus cosine squared. Sine squared plus cosine squared is 1, identically. So we'll just write 1 plus 16 t squared. Don't have to do much more to it than this, but 16 plus 16 t squared. If you really want to, you can clean up a bit more and say this is 16 times 1 plus t squared, which is just 4 times the square root 1 plus t squared. as much as you can simplify. And this gives you the speed of the particle, whatever it was, speed of the particle for any given time. That was part B. Now part C says, express the distance the particle travels along the path for 0, t between 0 and 2 as an integral. You need not evaluate the integral. So this final answer just becomes the integral 0 to 2 of your speed function. And that's it. That would be your distance, total distance.